Chapter 37, Interference of Light Waves. Problem number 1. A laser beam, wavelength 694 nanometers, is incident on two slits 0.1 millimeters apart. Approximately how far apart, in meters, will the bright interference fringes be on the screen 5 meters from the double slits? Alright. We have ourselves a double slit diffraction pattern, and let's think about what's involved here. First of all, well, let's set this up. We have monochromatic, coherent light incident on this double slit. What does that mean? If I say that light is monochromatic, that means it has the same wavelength. So we want to make sure that the light that's incident, that's going to hit these two slits and coming out, they both have the same wavelength. But with the light is also going to be coherent, which means that when the light hits these two slits, that they're exactly in phase. The coherent means they're exactly in tune with each other. Now, in order to do that, what Young did was he had another slit over here, just a single slit, and he had the light of one color, one wavelength, hit that slit, and when it came out, then it was all in phase, and so it was coherent. And so when that light hit the double slit pattern, you had two sources that were not only in tune with each other, but also having the same wavelength. What we could do today is, instead of having this single slit before that, we might just have a laser and have a laser beam hit the two slits at once, and that would be both monochromatic and coherent. All right, now that that's been said, here's our situation. We've got a double slit, and we've got some screen over here, and I need another screen over here. Screen over here, and we are some distance L away. The distance between these slits is D. They're really very, very close together, so this is really exaggerated right here. And there's going to be a pattern that comes off here, and there's going to be a pattern that comes off here, and it's going to hit at some point, and we're going to have some interference at that point, which we're going to say is some distance y from the middle of the screen. So if we say that the angle to that point between center between these slits and to that point is theta, then we might have a situation that looks something like this. Now, if these two slits were to converge right in the center here, they would be totally in phase, and we would have constructive interference right at that point. If it were to hit there, that would go the same length, that would go the same length. Since they're coherent, monochromatic, we'd have constructive interference, we'd have a bright fringe right in the center there. That would be our main maximum. But if we want a bright fringe to occur some distance up this way, then what we need is for the path length between these two sources of light to be an integral number of wavelengths. In other words, if the path length is a wavelength off, then we'll be assured that when they finally hit, they will be in phase, in tune with each other, and hence constructively interfere. So what we're going to have here is that if I drop a line here, making the residual paths from this point the same lengths, so that our only path difference is this right here. So I'll say that if that distance right there is an integral number of wavelengths, then we'll have constructive interference at that point y up there. Well, this angle here is the same as the angle theta here. And this hypotenuse of this little triangle, which is a right triangle, is distance d. So this distance right here is actually equal to d sine theta. So I can say that d sine theta equals an integral multiple wavelengths for constructive interference. Now, What I could also say is, looking at this big right triangle here, that y over L is equal to the tangent of theta. But theta's, in all these cases, theta is really small, because these fringes are only occurring, they're occurring really relatively close to that central fringe. So all these angles are much less than 10 degrees. And if you have that situation, then the tangent of theta is approximately equal to the sine of theta. If you're less than 10 degrees, they're small angle approximation. Those are the same. So what I can say is then that y over L is approximately equal to the sine of theta. And I'm going to put that then in for that. And what I'll get is now that d times y over L equals n lambda, or y is going to equal lambda L over d times m for constructive interference. For destructive interference, I want them to be half wavelength off, so if I did the same figuring, it'd be one phase, half of a phase length off. So I would end up with this, y equal lambda L over d, m plus 1/2. I should say that m is equal to 0, 1, 2, 3. And this would be for destructive interference. Usually I'm not going to lecture before I do a problem set, but I thought that was important to state. Let me see what else I might want to talk about. In this case, in problem number 1, our wavelength is 694 nanometers, which would be 6.94 times 10 to the minus 7 meters. And two slits are 0.1 millimeter apart, so D is 0.1 millimeters. So that's going to be 1 times 10 to the minus 4 meters. And we want to find approximately how far in meters will the bright interference fringes be when L is equal to 5 meters. And we're asked how far apart the fringes are going to be. Here's where the fringes are, but what we want to know is delta Y. You know, the difference between successive fringes. Now, if I were to take delta Y on, say, constructive interference, it would look something like this, lambda L over D delta M. And if I took successive delta Y's, it would be delta M. And in fact, that would be the same result I'd get from successive dark fringes. And this delta M is just 1. That's just the change in number from 1 to 2 to 3 to 4. So the difference between two successive fringes is going to be a wavelength times L times D. There's an interesting sidelight to this, is that if I were to rearrange this, I would get that the wavelength is equal to D times the change between the two fringes over L. And hence, if I set up a double slit diffraction pattern with a slit difference of D and my screen distance L away, if I measure the distance between fringes, then I could plug in what I know for D, what I know for L, and that measured delta Y, and I can measure the wavelength of the light. So that's kind of a neat little thing. That's one way to find the wavelength. All right, back to the problem. We want to find delta Y. how far apart the fringes are. So we want this formula right here. Delta y equals lambda L over D. So in this case, that would be 6.94 times 10 minus 7. L was given as 5 meters, and D is 0.1 millimeters, 1 times 10 minus 4. So if I put all those numbers in, I get 0.0347 meters, or 3.47 centimeters. So my answer would be answer B. Problem number 2, estimate the distance in centimeters between the central bright region and the third dark fringe on a screen 5 meters from 2 double slits 0.5 millimeters apart, illuminated by 500 nanometer light. Here's problem number 2. We want to find the distance between the central bright region and the third dark fringe. Now, the distance to each dark fringe is our same L over D, lambda, n plus 1/2. That's for dark fringes. And this will be the distance from the central maximum as it is. So we don't have to think about find the position of the central maximum. This is from that central maximum as it is. And in this case, m is equal to 0, 1, 2. So the first dark fringe would correspond to m equals 0. The second one would be m equal 1, and the third one will correspond to m equal 2 on this. So, so the m we want is m equal 2 for the third dark fringe. A little tricky there with the wording. All right, so let's figure out what that is. Let's put in our numbers. Y will equal L. L is given as 5 meters. The wavelength is given as 500 nanometer light. 500 nanometers. The distance between the slits is 0.5 millimeters. And m is 2, so I'll put that in there. And if I put all those numbers in, I get 0.0125 meters, or 1.25 centimeters. So the difference to the third dark fringe, the distance is 1.25 centimeters. Problem number 3, light is incident on a double slit. The fourth bright band has an angular distance of 7 degrees from the central maximum. What is the distance between the slits in micrometers? Assume the frequency of the light is 5.4 times 10 to the 14 hertz. One last point on that last problem before this, they said the third dark fringe. So you have a situation with these double slit patterns where light is actually canceling out light. One source is canceling out the other. And in that sense, this double slit diffraction is the best proof for the wave nature of light, because you cannot explain this effect using particles. Particles of light can't cancel each other out, and only waves can cancel each other out. So even though light has a dual nature, this experiment is demonstrating the wave nature of light. All right, back to problem 3. We've got a fourth band, and we're at 7 degrees from the central maximum. The frequency of light is given as 5.4 times 10 to the 14 hertz. So let's find the wavelength. We know that the velocity of light is the wavelength times the frequency, so the wavelength will equal the velocity of light divided by the frequency, 3 times 10 to the 8th meters per second, over 5.4 times 10 to the 14 per second. And this would give us a wavelength of 5.56 times 10 to the minus 7 meters, which is 556 nanometers. So that's our wavelength. What else is given in the problem? We're told that the angle theta is 7 degrees. So we'll be dealing with that. And I think we want to find the distance between the slits. All right. What we can do from this point is one of a couple things. We could say this. Since y over L is equal to tangent theta, and tangent theta is equal to sine theta, which is equal to m lambda over d, we could say y over L is equal to m lambda over d, or, did I do that right? So, yeah, so solve this for d. So d we call m lambda over tangent theta. That's the distance between the slits. So this is going to be m. So in this case, we're looking at the fourth bright band. And the fourth bright band is referring to the bright bands after the central maximum. So in this case, m actually is 4. So we've got 4 times 5.56 times 10 to the minus 7 over the tangent of 7 degrees. It wouldn't matter whether this was tangent 7 degrees or sine 7 degrees. So if I had used this, that would have been the same. They'll get the same number for that. And that comes out to 1.81 times 10 to the minus 5 meters. Or in micrometers, that would be 18.1 micrometers. The distance between the slits is 18.1 micrometers. On number 4, for small angle approximations, A, the angle must be 10 degrees or less. End of story. Problem number 5. 2 slits separated by 0.1 millimeters are illuminate with green light, wavelength of 540 nanometers. Calculate the distance in centimeters from the central bright region to the fifth bright band if the screen is 1 meter away. All right, so on this problem, number 5, the distance is given as 0.1, distance between the slits is 0.1 millimeters. And we have green light, wavelength of 540 nanometers. And we want the distance from the central bright region to the fifth bright band. So the central region is, the central region, m equals 0, and the fifth bright band will be m equal 5. So what we're looking for is the distance to the band where m is equal to 5. And the screen is 1 meter away. So there we have it. From our derivation before, we had y over L, which is equal to m lambda over d. So y is going to equal lambda L over d times m for bright fringes. So in this case, this will be 540 nanometers times L, which is 1, over D, which is 0.1 millimeters, times M, which is 5. If I put all those numbers in, I get 0.027 meters, or I could write that as 2.7 centimeters. So we'll find the fifth bright fringe, 2.7 centimeters, about an inch from the central maximum. If if we're 5 meters away. Problem number 6. Two slits separated by 0.05 millimeters are illuminated with green light, wavelength of 540 nanometers. How many bands of bright light are there between the central maximum and the 12 centimeter position? The distance between the double slits and the screen is 1 meter. All right. Well, starting from this same formula here for our bright fringes, let's come up with a value for m that will put us at the 12 centimeter position, and it won't be, if we do it this way, we won't come up with the integer, but we'll come up with a number, and then we can truncate that off to find the integer number that would be up to that fringe. So let's solve this for m. So m will equal lambda L over d y. And if I put in the values, can I do that right? No, it should be the other way around. dy or lambda L. If I put in the values, I'm going to have our d distance was given as 0.05 millimeters. So that's going to be 5 times 10 to the minus 5 meters. Our y distance is 12 centimeter position. So that's going to be 0.12 meters. Our wavelength was green light, 540 nanometers. And our distance to the screen was 1 meter. So if I put all that in there, I get 11.11, which means that at 12 centimeters, if we were to hit that point, we would want m to be 11.11, so that we're actually including 11 bright bands up to that point within that 12 centimeters. So that's our answer, 11 bright bands, C. 7. Two slits are illuminated with green light, wavelength of 540 nanometers. The slits are 0.05 millimeters apart, and the distance to the screen is 1.5 meters. At what distance, in millimeters, is the average intensity 50% of the central maximum? All right. For this one, let's think a little bit more theory again. Recall that when we had our two slits, we've got these things coming out like this. And what we could say is that there's a path length difference. So we have a phase difference. Well, the path length here is equal to m lambda, and that's equal to d sine theta, where this is d and this is theta. And we have a right triangle here, so that's d sine theta. And I want to say that this length, in relation to the wavelength itself, would create a phase difference, so that the ratio of this path length to the wavelength is equal to some phase difference, phi, over 2 pi. In other words, this fraction of wavelength will get us some fraction of a total circuitous 2 pi phase angle. So I can say that this phase angle is actually equal to sigma, which is d sine theta, over lambda times 2 pi. All right, so far so good. But that phase angle comes into play with the intensity. The intensity is equal to the maximum intensity times the cosine square of this phase angle divided by 2. That's something I'm not going to derive here, but it has to do with the fact that the amplitude of these two waves are interfering, and when you add those together in a time average, you come up with this result. So I'm going to put this phase angle in there, and what am I going to get? It's going to be I maximum cosine squared 2 pi d sine theta over 2 lambda. Q's cancel out. So my result is the intensity at any particular point is the maximum intensity times the cosine squared of pi d sine theta over lambda. Or what I could also use is, since the sine of theta is equal to, as we extend this out to the screen here, this distance is y, and this is L. The sine of theta, some distance y, is going to be equal to y over L. So this is one form that we want to use. Another form would be this. Where I've substituted y over L for theta there. So this is just showing the variance of intensity along this wall here. In other words, we got a maximum here, and then we're just kind of going like this along that wall according to the cosine squared of this. All right, so with that little sidelight, let's look at problem number 7. Again, what's given in this problem? It said 2 slits are illuminated with green light, so the wavelength is 540 nanometers. .4 times 10 minus 7 meters. The slits are 0.05 millimeters apart, so D is 0.05 millimeters, which is 5 times 10 minus 5 meters. The distance to the screen is 1.5 meters. And what distance is the average intensity? 50% of the central maximum. So we're saying the intensity is equal to 50% or 0.5 I max. That's the information given. So let's put that in there and see what it looks like. So we've got 0.5 I max equals I max times cosine squared. So let me do that. Cosine squared of all this. We've got pi times d times y, which is what we want to find, over lambda times L. I suppose I didn't have to put all the numbers in yet, but this kind of helps. I maxes cancel out. Let's take the square root of both sides. And so I have the square root of 0.5 equals cosine of all that stuff. Let's take the inverse cosine of both sides. So I have the inverse cosine of the square root of 0.5 equals all those numbers. Let's put them in again. And solve this for y. So we got, normally I don't do it this way, but that's okay. 1.5, 5.4 times 10 to the minus 7, cosine inverse of the square root of 0.5 over pi over 5 times 10 to the minus 5. If I do all that, I get 3.92 times 10 minus 3. Or 3.92 millimeters. Make sure that when you do this, and you do that inverse cosine of 0.5, square root of 0.5, that you're in radians mode, because that's the number you want. You don't want that to come out in degrees. And so you're in radians mode when you do that. Come up with this answer. Answer given is 4 millimeters. So let's close to 3.92. Problem number 8. Two slits are illuminated with red light, wavelength of 650 nanometers. The slits are 0.25 millimeters apart, and the distance to the screen is 1.25 meters. What fraction of the maximum intensity is the intensity measured at a distance of 3 millimeters above the central maximum? All right, at number 8 here, we want the fraction of the maximum intensity at these conditions. We basically want to use this last formula that I derived over here. So we'll say that the intensity will equal I max cosine squared pi slit distance, y distance, over the wavelength times the distance to the screen. And in this problem, we're given all these factors here, so we just need to plug that in. So what we have is this is equal to I max cosine squared. The slit distance was given as 0.25 millimeters. 0.25 millimeters. We are 3 millimeters above the central maximum, so that's y. The wavelength was given as 650 nanometers. And the length to the screen was given as 1.25 meters. So I'm going to put all those numbers in, take the cosine squared of that, making sure I'm in radians mode on my calculator. Then this comes out to I max times 0.943. So our intensity at that point is 94.3% of the maximum intensity, 0.943. Answer A. Number 9. In a double slit experiment, the distance between the slits is 0.2 millimeters. The distance to the screen is 150 centimeters. What wavelength in nanometers is needed to have the intensity at a point 1 millimeter from the central maximum be 80% of the maximum?
Right.
Okay, for this one, number 9, I guess we're going to reverse engineer the previous problem. So we have I equals I max cosine squared pi dy over lambda L. And we are given the slit distance, 0.2 millimeters. We're given the distance to the screen, which would be 1.5 meters. We're given the y distance, which is 1 millimeter at the point, and we're given that the intensity is 80% of the maximum intensity. So we want to reverse engineer this for the wavelength. So I'm going to say this is 0.8 I max equals I max cosine squared of all this stuff. Get rid of the I max, take the square root of both sides. So we have, and take the inverse cosine of both sides as well. So I have the inverse cosine of the square root of 0.8 equals everything in that parentheses. Solve this for lambda. So I have lambda will equal pi dy over L times the cosine inverse of the square root of 0.8. Remembering when we do the inverse cosine that we are in radians mode, so you don't come up with degrees on that. And if I put in our numbers then, this would be pi times the slit distance, which was 0.2 millimeters, or 2 times 10 to the minus 4 meters. The distance to that point was 1 millimeter, so that's going to be 10 to the minus 3 meters. The screen was 150 centimeters away, so L is going to be 1.5 meters. And then we have cosine inverse of 0.8. put all those numbers in, I get 9.03 times 10 to the minus 7 meters, or 903 nanometers. Closest answer is A, which is 900 nanometers. Number 10, in a double slit experiment, the distance between the slits is 0.2 millimeters. The distance to the screen is 150 centimeters. What is the phase difference in degrees between the two wavelengths arriving at a point P if the angular distance of P is 10 degrees relative to the central peak and the wavelength is 500 nanometers? Convert your results so the angle is between 0 to 360 degrees. All right, and this one, we had derived the expression for the phase difference. We had said that that was equal to 2 pi sigma over lambda, which is 2 pi d sine theta over lambda, sine theta being y over L. I'm going to need that in this one? No? I can leave it like that. So that's our phase difference. And if we put in our numbers on this one, then we have the phase difference is 2 pi. The slit distance is 0.2 millimeters. So that's 2 times 10 to the minus 4 meters. Our angle is 10 degrees, so that's going to be sine of 10 degrees. I can use degrees there because I'm taking the sine of it. The wavelength is 500 nanometers. And I'm going to get a fraction here, or a number here in radians. That's going to be 436.43 radians is our phase difference between the two sources. Now, knowing that there's one cycle for every 2 pi radians, let's see how many cycles this is. So let's convert this and say there's, we call it 1 revolution if you wish, for 2 pi radians. So we'll divide by 2 pi, and that would give me 69.459 revolutions or cycles. So we have 69 cycles, and then we have this extra fraction, this 0.459, which is the fraction of one cycle that we've gone through. So that's what we want. In other words, our extra phase is equal to 0.459 of a revolution, or one cycle. Now, if we say that one cycle is 360 degrees, then our extra phase is going to be 0.459 revolutions times 360 degrees per revolution. And that will give us our phase difference in degrees, which is 165.3 degrees. So that is our result as an angle between 0 and 360 degrees, 165.3 degrees. Fun? Number 11, in a double slit experiment, the distance between the slits is 0.2 millimeters and the distance to the screen is 100 centimeters. What is the phase difference in degrees between two wavelengths arriving at a point 5 millimeters above the central maximum if the wavelength is 400 nanometers? Convert your result so that the angle is between 0 and 360 degrees. All right, well, this problem is similar to the last one, where we had phase difference is 2 pi d sine theta over lambda. In this case, we weren't given a theta. We were given the point on the screen where we're comparing these two wavelengths where the two signals come in together. And that point is a y distance. So I'm going to convert the sine theta, saying that sine theta is essentially equal to y over L. I'm going to put that in there. And so now we'll say our phase difference is going to be 2 pi dy over lambda times L, where I basically put in that for the sign at the end. All right, so let's figure out this. It's going to be equal to 2 pi. The slit width was 0.2 millimeters. Our distance up on the screen, y, was 5 millimeters above the central maximum. The wavelength was 400 nanometers. And the distance to the screen was 100 centimeters, so we'll put that as 1 meter. And so this will give us the phase difference in radians. And if I put all those numbers in there, I get 15.71 radians. Now this is, we want this in terms of cycles, so we want to see how the two signals compare and whether or not they're in sync or how much out of sync they are. So let's put this in terms of revolutions like we did in the last problem. We'll say that there's 1 revolution for 2 pi radians. And we'll divide this by 2 pi. If I do that, I come up with 2.5 revolutions, or 2.5 cycles. Now what I probably should have done is, what does this really mean? Okay? And if we're coming up to a point where we've got one signal coming in like this, another signal coming in like this, you know, they're monochromatic, so they have the same wavelength, but they're now going to converge and be out of phase. What 2.5 cycles means is that maybe this longer one has an extra path length of 2.5 wavelengths. Right? So 2 cycles would be okay, you'd still be in sync, but that extra leftover amount, the half a revolution, is what's putting it out of phase. So it's going to be half of a cycle out of phase, is what it means. So whatever's the integer amount, we can just lop that off. Because what's important is the extra amount left over. So our extra phase is going to be 0.5 revolutions, but we want to find that in terms of 0 to 360 degrees. So we'll say there's 360 degrees per revolution. And how am I going to write this extra phase? Prime. So we'll say that's 180 degrees. So they're actually, this probably is going to be a minimum where the two interfere and come up with destructive interference. 180 degrees phase difference. Problem number 12. An interference pattern is produced at point P on a screen as a result of direct rays and rays reflected off a mirror as shown in the figure. If the source is 100 meters to the left of the screen, 1 centimeter above the mirror, and the source is monochromatic, a wavelength of 500 nanometers, find the distance y in millimeters to the first dark band above the screen. All right, here's our setup. We've got a source here. Down here we've got a mirror. And over here we've got a screen. And here's our source. This is a mirror. And what we're going to do is we're going to actually have interference between the direct ray of the source and the reflected ray off the mirror. So if we were going to some point up here, we might have a reflection. And so those two signals from the same source are going to interfere on that point. Now, what's going to happen, though, is when this light reflects off the mirror, it will invert. So there will be one inversion due to reflection, 180 degrees out of phase. And the basic effect is the same as that of a double slit diffraction pattern. If we can imagine that the reflected light were actually coming from another source down here where the image is, except that we already have an inversion due to the reflection. This pattern is called Lloyd's mirror with a one-phase reversal. And if we are 1 centimeter away from the mirror, then essentially our D is going to be twice that distance that we are from the mirror. So the D is going to be equal to 2 times 1 centimeter, or 0.02 meters. We can treat it like a slit of that width. But the other thing is, for dark fringes, we'll have the same result as we had for light fringes before, or bright fringes before, which is that will be equal to lambda L over D times M. And for bright fringes, that will be the same as what we had for dark fringes before. So that will be lambda L over D times M plus 1/2. The same idea, only these two results flip because of the inversion of the reflected light there. So let's see how that works in this problem. We want to find the distance to the first dark band, which would correspond to M equal 1 in this case. So Y dark will equal lambda L over D, because the central band will be a dark band, and that will be M equals 0. So we want to find this when M is equal to 1. And our wavelength was 500 nanometers. The distance to the screen was 1 meter. 100 meters, I'm sorry. The slit distance is 2 centimeters, or 0.02 meters. And M is going to be 1. Put all those numbers in, and I get 2.5 times 10 to the minus 3 meters, or 2.5 millimeters. Answer in millimeters, answer D, 2.5 millimeters. Problem number 13. An interference pattern is produced at point P on a screen as a result of direct rays and rays reflected off a mirror, as shown in the figure. Now, the source is 100 meters to the left of the screen, 1 centimeter above the mirror, and the source is monochromatic of wavelength 500 nanometers. Find the distance y in millimeters to the first bright fringe. All right, so this is the same setup for the problem as the previous one, only we want to find the first bright fringe. Now, if we look at the formula for the previous problem, the first bright fringe will correspond to M equals 0, because we'll actually get a bright fringe off the central maximum at that point where M is equal to 0. So the first bright fringe will correspond to M equals 0. That's a key aspect, and the rest of it should follow then. So we have Y bright is going to equal lambda L over D times M plus 1/2. So this is going to equal the wavelength, which is 500 nanometers. We are 100 meters away from the screen. And the distance to the mirror was 1 centimeter, but our distance D we're talking about here is our prescribed distance, which would be to this image down here, which would be 2 centimeters. And of course over here we're going to have 0 plus 1/2, or M equals 0. Now put all those in there, I get 1.25 times 10 to the minus 3 meters, or 1.25 millimeters, which happens to be half of what we got for the distance to the first dark maximum from the central maximum, which makes sense. We should be halfway in between for every successive dark to bright fringe. 14. An interference pattern is produced at a point P on a screen as a result of direct rays and rays reflected off a mirror as shown in the figure. If the source is 100 meters to the left of the screen, 1 centimeter above the mirror, and the source is monochromatic of the same wavelength, 500 nanometers, find the condition for maximum brightness on the screen in terms of theta, lambda, and D. All right, on number 14, we want to find the condition for maximum brightness on a Lloyd's mirror type situation, just like we've done in the last two problems. Essentially, let's look this up again. Here's our mirror Here's our screen. Here's our source. And again, we're coming to some point there. We're reflecting out this mirror to that same point. We've got an image down here, so we call this distance D, which is twice the distance from the source to the actual mirror. And for interference to work, we want this path length here to be an integral number of wavelengths, but in this case we want maximum brightness, and we know that there's going to be an inversion on this reflection. So we want this path length here, which would be, see, D is the distance, D is the distance to the mirror, so this is actually 2D in this case. So this distance here is going to be 2D sine theta, where this is theta. All right, that makes sense. So we want 2D sine theta to be a half number of wavelengths because we're getting a half wavelength due to the inversion here. We want to have constructive interference. So we need to have the path length provide another half wavelength difference. So this will give us constructive interference. And that's where M is going to be equal to 0, 1, 2, 3, so forth. And so that's it. That's B. We want 2D sine theta to equal n plus 1/2 times the wavelength. 15. An interference pattern is produced at point P on a screen as a result of direct rays and rays reflected off a mirror as shown in the figure. If the source is 100 meters to the left of the screen, 1 centimeter above the mirror, and the source is monochromatic, 500 nanometers, find the conditions for minimum brightness on the screen in terms of theta, lambda, and D. Yep. Okay, so this is kind of similar to the last problem. We're going to just look at it again here. We've got a mirror, a source, and a screen. And imagine that we're going to invert upon reflection off the mirror. This distance here is D. So the distance between the image and the source here is 2D. Now in this case, we want the condition for minimum brightness on the screen. Now this path length difference here is going to be 2D sine theta, where this is theta. And in order for us to have a minimum on this screen, we want the path length to be an integral number of wavelengths so that, at least as path is concerned, we are totally in phase with the two signals. So the only thing that's making these two signals out of phase is the fact that we have this one inversion upon reflection. So we want the path length to actually correspond to an integral number of wavelengths so that we will have destructive interference due to just the one inversion upon reflection. So this will give us destructive interference. And so that condition would be under B, 2D